In this class, we will discuss about the concept of conservation of linear momentum and its application. So, what is conservation of linear momentum? You know what is linear momentum? It's a property of a moving particle which is acquired by its mass and its velocity, and it can be measured as a product of its mass and velocity. So, if a force F acting on a particle of mass m, then according to Newton's second law of motion, we have force, we can represent force as the rate of change of its linear momentum. This is Newton's second law of motion, and P is mv. P is the linear momentum, which is m into v, mass into velocity. So we can substitute mass into velocity instead of p. So we will get d by dt of m into v. Or p is equal to mv is the linear momentum of the particle. Momentum is a vector quantity, so that's why we are using the vector symbol here, since v is a velocity is a vector quantity. If the external force acting on the particle is 0, then we can write f is equal to dp by dt is equal to 0, which means the rate of change of momentum is 0, which means p is a constant or mv is a constant. Thus, in the absence of an external force, which means f is equal to 0, the linear momentum of a particle remains constant. This is the conservation of linear momentum. That is, in the absence of any external force, the linear momentum of a particle remains constant. Now let us consider a system of n particles whose masses are m1, m2, etc., mn. The system can be a rigid body in which the particles are in fixed positions with respect to one another, or it can be a collection of particles in which there may be all kinds of internal motion. So we are considering now a system of particle, that is a rigid body in which a number of particles m1, m2, etc. are distributed, which are distributed in fixed positions, or it can be a collection of particles where there can be all kinds of internal motions. This is the system we are considering here. Suppose that the particles of the system are interacting with each other and are also acted by external forces. So if you are applying an external forces on this system, and also there are internal forces acted on these particles of this system. If P1 is equal to M1 V1, P2 is equal to M2 V2, etc., Pn is equal to Mn V1, Mn Vn are the moments of the particles of masses M1, M2, etc., Mn respectively. So the system is consisting of n number of particles having masses M1, M2, M3, etc., Mn. So when they are interacting by internal or external forces, they will achieve a momentum which can be represented as m1 v1, m2 v2, etc. Okay. Then the total momentum of the system will be the vector sum of the momenta of individual particle. So the total momentum of the whole body can be represented as the sum of the individual momenta of the particle consisting of the body. So this is P1 plus P2 plus P3 plus etc. Pn. And this P1, P2 are represented as M1, V1, M2, V2, etc. So if we differentiate this equation with respect to time, we will get dp by dt is equal to dp1 by dt plus dp2 by dt, etc., dpn by dt. This dp by dt is nothing but the force according to Newton's second law of motion. So we can write F1 plus F2 plus etc. Fn, where F1, F2, etc. Fn represents the forces on the particles of masses m1, m2, etc., mn respectively. So these are individual forces acting on this particles of the system, m1, m2, etc. So these forces include external and internal forces both. So these forces can be internal and external forces. But according to Newton's third law, the internal forces exist in pairs of equal and opposite forces. They balance each other and so do not contribute anything to the total force. You know what is Newton's third law? That is, every action has an equal and opposite reaction. So in the internal forces of these particles, there can be a pair of opposite forces also. So the forces, internal forces between two particles are exist in pairs always inside the body. So if we take the system as a whole, the sum of the internal forces will cancel each other because they are exist in pairs and they are equal and opposite, so they will cancel each other. So the total contribution of the internal force contribute nothing to the total force. Hence the right hand side of the above equation represents the resultant force F external only due to the external forces acting on all the particles of the system. So since there is no internal force contribution to the system, the total force represents only the external force acting on the system. The internal forces cannot change the total momentum of the system because being equal and opposite. So because of this equal and opposite pairs of the forces, the internal forces cannot contribute anything to the total momentum of the system. Okay, hence if we want to change the total momentum of the system of the particles, it is necessary to apply external forces on that system. So if we want to change the momentum, total momentum of the system, we have to apply an external force. So because there is no internal contribution from this system of particles, then the sum of the external forces can be written as F external as dp by dt, which is equal to d by dt of p1 plus p2 plus etc. pn. If the resultant external force is 0, then we can write dp by dt as 0 or p is equal to a constant, which means p is not varying. That is the time variation of p is 0 means p is constant. So the total momentum can be represented as the sum of the individual momenta p1 plus p2 plus p3 etc., which is a constant. So which means the resultant external forces, if the resultant external forces acting on a system of particle is 0, the total linear momentum of the system remains constant. This simple but quite general result is called the law of conservation of linear momentum for a system of particles. So we have stated already what is law of conservation of momentum. That is, if the external force acting on a particle is 0, the linear momentum remains constant, which is known as law of conservation of linear momentum. So what is law of conservation of linear momentum of a system of particles? That is, we have seen that when the external force acting on the system of particle is 0, the sum of the total linear momentum of the system remains constant. This is known as law of conservation of linear momentum for a system of particles. It is to be noted that the momenta of individual particles may change, but their sum is, that is, the total linear momentum remains unaltered even in the absence of external force. So if a system consists of n number of particles or whatever number of particles present in the system, the individual momenta may vary, but the total sum of the momenta of the system always remains constant even in the absence of external force, which is known as law of conservation of linear momentum for a system of particles. The law of conservation of momentum is a fundamental and exact law of nature. No violation of it has ever been found, and it has been thoroughly checked by all kinds of experiments. We have established this law on the basis of Newton's laws, but this law holds true where Newtonian mechanics fails. Actually, the law of conservation of linear momentum is one of the sacred laws of nature and is a proof of on itself. So, law of conservation momentum is a fundamental and exact law of nature. This is verified by all many experiments. Okay, so this is about law of conservation of linear momentum. Now, where we are applying this conservation of linear momentum. So, an example is rocket propulsion. So, the rocket works on the principle of jet propulsion. The word jet means a high velocity streams of fluid issuing out of a nozzle or orifice. So, you may be familiar with the word jet, which means a high velocity stream of fluid issuing out of a nozzle. Nozzle means a narrow opening. So when a stream of gas or air is pushing out through this narrow opening, its velocity can be very high. So that flow is known as a jet. So rocket works on the principle of jet propulsion. The method of driving a body or machine through the agency of jet is called jet propulsion. So what is mean by, we have seen what is jet and what is meant by jet propulsion. So the method of driving a body or machine through the agency of jet is called jet propulsion. So the principle using jet, the body which is moving using the principle of jet is known as jet propulsion. The principle of jet propulsion depends on the law of conservation of momentum, according to which the momentum of jet emerging from a body in the backward direction is equal and opposite to the momentum of the body in the forward direction. So the rocket is working on the principle of jet propulsion, and the jet propulsion depends on the law of conservation of momentum, which means where the momentum of jet emerging from a body in the backward direction. If the gas or the stream of gas is propelling out in the backward direction, and it will be in equal and opposite to the momentum of the body in the forward direction. So this is the principle. So we can see now how the rocket works. In a rocket, I have shown here a picture. In a rocket, the fuel and the oxidizer are burned in the combustion chamber. So this is the combustion chamber. So the fuel and oxidizer are burned in this chamber. The heat of combustion makes the pressure very high inside the chamber, so that a jet of hot gases emerges from the tail of the rocket with a very high velocity. So this is a nozzle or narrow opening, and the fuel and oxidizer is the combustion takes place inside this chamber of the fuel and oxidizer. So whenever this combustion takes place, it will produce a high pressure inside this chamber. So the gas will propel out through this narrow opening, which will produce a jet. Okay. So the jet will, a stream of gas will emerges out through the narrow opening with a very high exhaust velocity, and in consequence the rocket moves in the forward direction. So you imagine the shape of the rocket. You have You may have seen it in TV or many medias. When the rocket is moving upwards, you might have seen the a very high velocity jet of air flowing out from the back of this rocket. It's due to this jet propulsion, jet of stream moving downwards, the rocket is moving upwards. So what is happening here is the fuel and oxidize this combustion is taking place inside this chamber, and a very high, and the air is propelled out through this with very high exhaust velocity, and due to this a very high momentum is imparted in the forward direction, so that the rocket move in the upward direction. According to the type of fuel used, rockets are classified as liquid fuel rockets and solid fuel rockets. So the fuel used in the rockets can be of different types, according to which the rockets can be classified as liquid type and solid fuel type. In the former type rockets, liquid hydrogen or liquid paraffin is employed as fuel, and liquid oxygen, hydrogen peroxide or nitric acid as oxidizer. So in the liquid fuel rockets, liquid paraffin or liquid hydrogen can be used as fuel, and liquid oxygen or liquid hydrogen peroxide or nitric acid as oxidizer. In the solid fuel rockets, the fuel, example gunpowder, itself contains the oxidizer, and therefore a separate combustion chamber is not needed. Okay, so this is the difference of solid and liquid type rockets. Let the mass of the so we have to find out, and now we will find out the final velocity of the rockets achieved when it is moving. For this, let us consider let the mass of the rocket at any instant t be m, and its velocity be v. Here this m and v are capital. We are using small letter m and v later, so that's why we are using capital M and v. So for at any instant, the mass and velocity of the rocket can be represented by capital M and capital V in the laboratory or initial frame of reference. If a mass m of the hot gases emerges out per second with exhaust velocity minus v, this is small letter v, related to the rocket, then the rate of change of mass of the rocket is given by dm by dt, which is equal to minus m. So what is saying here is when the fuel burned inside the combustion chamber, a gas with high pressure will propel out through the nozzle. So if the mass is m of the hot gas emerges out per second through the exhaust valve, and v is its velocity. Here a minus, we have put a minus sign here because it is moving in the backward direction. Due to this velocity of this exhaust fuel, the rocket will be moving in the forward direction. So the velocity of the exhaust gas is represented as minus v relative to the rocket. That is, we are saying here relative to the rocket. So the rocket's motion is in forward direction, the jet motion is in backward direction. That is why a minus sign here with respect to the motion of the rocket. So m is the mass of the jet, and minus v is its relative velocity to the rocket. Then the rate of change of mass of the rocket is dm by dt. So m is the mass of the rocket. So the rate of change of mass of the rocket can be represented as dm by dt. which is equal to minus m. This is because when the fuel burns, the mass of the fuel decreases. Here m is the mass of the fuel. So when the fuel burns inside the combustion chamber, the mass of the fuel decreases. So when the mass of the fuel decreases, the mass of the rocket as a whole decreases. So that the change of the mass of the rocket can be represented as the change in the or the decrease in the fuel mass. That's why it is represented as minus m. Now assuming small v and capital V parallel, though they are in opposite direction, capital V is the velocity of the rocket and V is the exhaust velocity of the gas. So though they are in opposite direction, they are in parallel. Now assuming they are the velocity small v and capital V are in parallel, the velocity of the gases in the laboratory frame will be minus v plus v. So the velocity of the gases you have seen in the frame of reference chapter, the laboratory frame, initial frame, etc. So I need not explain it here. So the total velocity of the in the laboratory frame can be represented as minus v plus capital V, and the momentum of the burnt fuel ejected per second will be m into minus v plus capital V. So since this is the total velocity of in the laboratory frame, the momentum can be represented as mass into velocity. So that will be m into minus v plus capital V. Hence force on the rocket can be represented as F is equal to d by dt of here d by dt is here. This is not simply minus m into d by dt of minus m into, that is the rate of change of momentum. Since dm by dt is minus m, we can substitute instead of minus m capital M. So we can write f as dm by dt into minus v plus capital V. So according to Newton's second law, f is equal to d by dt of m into v, mass into velocity. This is the momentum of the rocket. So we can write d by dt of mv. So the left side is d by dt of mv, which is equal to dm by dt of minus v plus v. So if we are expanding the bracket, that is differentiate, this is the we have to apply a product rule here. So m into d by dt plus v into dm by dt will become minus v into dm by dt plus v into dm by dt. So that will give you m into d by dt is equal to minus v into dm by dt, because these two terms will cancel each other. So the remaining term will be these two. So we will get this equation. This equation gives the instantaneous force on the rocket. From the above equation, we get dv is equal to minus dm by m. So this equation gives the instantaneous force on the m into dv by dt is the mass into acceleration. This is the force. So this represents the instantaneous force acting on the rocket by the combustion of the fuel inside the rocket. From this equation, we can write dv as minus dm by m into v. Since the dt term here, so we can represent this equation like this. So if we are integrating this equation on both sides, we will get v on left side, which is equal to, if we are integrating this term, we will get v log m, logarithm to the base e m plus the constant of integration. So we have to find out the constant of integration by putting the initial condition. So if initially mass of the rocket is m0, we are taking the initial mass of the rocket as m0 and velocity as capital V0. Then if you are putting this value in the equation, we will get V is V0 and M is M0. So what we will get? We will get this equation like this. Or we can write C as V log M0 plus V0. And putting back this constant of integration into the equation of the velocity, we will get V is equal to minus V log to the base M plus the constant of integration. Constant of integration is now this value, and we will get like this. Now we can write these two terms together. This is log A plus log AB form. Log A plus log B form, which can be written as log A by B. So V is equal to V0 plus V log M0 by M. So from this equation, we can understand that to achieve a high final velocity of the rocket, it is necessary that the value of exhaust velocity, this is the exhaust velocity, should be very large, because this is in linear relationship with the final velocity. So this is the velocity of the rocket achieved. This is the initial velocity of rocket. This is the final velocity achieved after the combustion of the fuel inside the chamber. Here small v is the exhaust velocity of the gas, and m0 initial mass of rocket, and m is the final mass of the gas. So if since the final velocity is in linear relationship with the exhaust velocity, a high velocity of the rocket can be achieved by two methods. By the value of the, by making the value of exhaust velocity v very large and the final mass very small. So the v should be very large, small v should be very large, and capital M should be small, since this is in the denominator, so this value will be high. Okay, so the magnitude of exhaust velocity depends on the nozzle design. Because when the combustion takes place inside the chamber, the pressure inside the chamber will become very high. So this very high pressure of the gas will push the gas outside the chamber through this nozzle. So the design of the nozzle will design the velocity of the exhaust gas flowing out from the chamber through this nozzle. So theoretically, the limit of exhaust velocity is equal to the root mean square velocity of the gas molecules at the temperature of the combustion chamber. Root mean square velocity means the average velocity of the gas molecules. The average is calculated as the root mean square of its root mean square of the root mean square method. So the theoretical value limit of the exhaust velocity equal to the root mean square velocity of the gas molecules at the temperature of combustion chamber. Now its practical limit is nearly 2 km per second, because it becomes difficult to attain temperature more than 3000 degrees Celsius. So since it is difficult to attain a temperature more than 3000 degrees Celsius inside the chamber, so the theoretical limit of attaining exhaust velocity is theoretical value is maximum 2 km per second. And practically the ratio of the initial and final mass m0 by m of the rocket has also an upper limit. In case of a single stage rocket, means which has only one engine, only one combustion chamber, etc. So the final mass m is mainly due to the fuel containers, and it cannot be smaller than 10% of m0. So the m0 here is the initial value, and m is the final mass. So making in order to attain a large velocity, we can make this value final mass as small value, but there is a limitation for making this value very small. So in case of single stage rocket, what happens is the final mass m is mainly due to the fuel because the complete fuel might have been burned completely, so the weight will be completely due to the fuel containers, and it cannot be smaller than 10% of m0. In the solid fuel rockets, final mass m may be smaller than this, but in such a case this advantage is upset by smaller exhaust velocity v, which affects in consequence of the final velocity. So a final mass which is very smaller than that acquired in a liquid fuel rocket can be achieved in solid fuel rocket, but there is a disadvantage because in the solid fuel rocket the exhaust velocity will be small. So we have to make the exhaust velocity large and the final velocity small in order to attain a large final velocity for the rocket. So the limitations are these two in order to attain a large exhaust velocity and a small final velocity. So if m0 by m is 10, which is the maximum upper limit, and initial velocity value is 0, and exhaust velocity small v is equal to 2 km second, which is again the upper limit of the exhaust velocity, then final velocity can be calculated using this formula by substituting these values. v0 is 0 and small v is equal to 2 and the ratio is m. So if we are substituting this value, we will get the final velocity of rocket as 4.6 km per second. So this velocity is much less than the average velocity or the orbital velocity near the surface of the earth, which is 8 km second. Hence such a large velocity cannot be obtained with the help of a one stage or single stage rocket. Employing 2 or 3 stage rockets, higher final velocities can be easily obtained. So by substituting the limitation value, the maximum value for exhaust velocity and the mass ratios in the final equation of velocity, we will get the maximum velocity as 4.6 km, which is very less than the escape velocity. Escape velocity is the velocity needed for escaping from the gravitational field of the earth. Since the velocity 4.6, which is 11 km, the escape velocity of earth is 11 km per second. So 4.6 km final velocity of rocket means which is less than the escape velocity of the earth, which means the rocket cannot be moved out of the gravitational field itself. So it's not sufficient to move the rocket outside the earth's atmosphere. So a single stage rocket cannot be used or cannot be obtained with a cannot be useful for propelling outside the earth's gravitational field. If you are using a multi-stage rocket, we can acquire high final velocities. So in a two-stage rocket, two rockets are connected in series. So here this is the first stage of the rocket and this is the second stage of the rocket. Here is the combustion chamber and the means fuel and oxidizer chamber, and here is the second stage chamber. So first stage rocket is large, this is large and heavy, and second stage rocket is comparatively small and light. This is the design of a two-stage rocket. When the rocket is sent in space, the first stage rocket is used first, and when its fuel is burned, it gets detached and is discarded. So this is a two-stage rocket. So what happens is the fuel in the first chamber will burn first, and after it's completely burned, this first part will be discarded from this or removed from this rockets, from this first part. So after the combustion of the fuel completely from the first chamber, the rocket will attain a final will acquire a velocity, and which will be the initial velocity for this second stage of this rocket. So with that high velocity as initial velocity, which the rocket can again attain a very high velocity after the second stage. That's the principle. So after the fuel is completely burned in the first stage, the first chamber is completely detached and is removed from the rocket. Now the second stage rocket starts on with the initial velocity v0 imparted to it by the first stage. That what I said here, said now. Hence, according to this equation, the velocity equation, the final velocity. So after the first stage, with the maximum limiting values for exhaust velocity and mass ratio, we will get the initial velocity as 4.6 after first stage. So now the for the second stage, the initial velocity will be 4.6. Now again for the second stage, we are substituting the limiting values for exhaust and mass ratio. So we will get 9.2 kilometers second, which is nearly twice the velocity achieved by only one stage rocket. So it will be slightly less than the double, because for first stage the ratio m0 by m will be somewhat smaller. It is due to the fact that in m the final velocity, final mass m of the first stage, the entire mass of the second stage remains included. Okay, so this slight variation is happening because the final mass of the m, the entire mass of the second stage remains included. So we can attain very high velocity if we are using multiple stages of rockets. So we have seen that in the single stage rockets, the final velocity of the rocket is only 4.6, and in the second stage it is, after the second stage it is 9.2. So if we are using multiple stage rockets, we can use high velocity for rockets. So this is the principle of rocket propulsion. Okay, I just worked on the principle of and momentum conservation laws, and the rocket is moving outward due to the high velocity jet flowing out from the nozzle in the backward direction, which will give a forward momentum to the rocket according to Newton's third law. So now we are considering the G factor, the acceleration due to gravity in the rocket propulsion. In the previous discussion, we have not considered the factor G, the influence of gravity on the rockets. Now we are considering the gravity also. So due to the gravitational force, a weight mg will be acting on the rocket. So we have neglected that term in the previous description. If the rocket moves vertically upwards, the force on the rocket is dm by dt into minus v plus capital V minus mg, because the gravitational force is acting downwards. The rocket is moving upwards. So this is the force acting on the rocket in the forward direction or upward direction, and this is the gravitational force acting on the rocket in the downward direction. So the total force can be represented as the sum of these two. Since these are in opposite direction, a minus sign is appearing here. So we can represent the force as, the total force as dm by dt of minus v plus v minus mg. So on simplifying this equation, we will get, so this equation can be expanded, m into dv by dt plus v into dm by dt, which is equal to, on the right side, here expanding this bracket, so we'll get these terms minus v plus capital V term minus mg. So this is, so these two terms, similar terms on both sides will cancel each other, so we'll get these remaining terms. Now integrate this equation. For integrating this, we can write this equation like this: m into dv as minus v dm minus mg into dt, and so dv will become minus v dm by m minus g dt. So just rearrangement of terms. Now integrating this equation, we will get capital V as minus v log m from this equation minus gt plus c. So in order to find the constant of integration c, we are putting the initial condition. When t is equal to 0, the initial mass is m0 and velocity v is equal to v0. So the constant of integration will get from this equation, t is equal to 0, so we will get v0 plus v log to the base e m0. Now putting back this constant of integration in this equation, we will get capital V as minus v log m minus gt plus v0 plus v log m. So this is again, these two term can be combined according to the logarithm rule, log a plus b or log a minus b as log a by b. So we can write v0 plus v log m0 by m minus gt, where t is the time required for burning the fuel. It is clear from this equation that if the time t is small, then due to attraction of the earth, the reduction in the value of v is negligible. So if t is small, the reduction in the velocity is very small. T is small means this value, this factor is reducing from this factor. So if t is, t small means this factor, this term, the product of this term is very small. This term is reduced from the combination of these two terms. So if t is very small, which means which does not affect much to the final velocity. So if the fuel burns very slowly, the rocket may not be able at all to rise, or it may keep hovering without attaining any velocity. And that means if the fuel burns very slowly means T is very large, so that means there is a reduction in the final velocity. There is much significant effect on the final velocity. Then that means the rocket will not attain much velocity to escape from the gravitational field of the earth. It will just hover without attaining any velocity. Hence, it is necessary that the fuel is burned rapidly in the first part of the journey. So the fuel should burn fastly, but the fuel should not be burned very rapidly. There is again a limitation for this. The fuel cannot be burned very rapidly, as it results the disadvantages in two ways. The disadvantages of burning the fuel rapidly are: one is, if the rocket acquires a very high velocity before it has moved above the atmosphere, there will be a greater wastage of energy due to air resistance. If the rocket is acquiring very high velocity, even before it escapes from the Earth's atmosphere, there may be air resistance offered by the atmosphere of the Earth. So a larger part of the energy acquired by the rocket may be wasted in order to overcome this air resistance. So this is one disadvantage. And the second disadvantage is, Due to its larger acceleration, the weight of the passengers may increase very large. So, the due to its when the rocket occurs very high velocity, due to a larger acceleration, the weight of the passengers may increase very large, which is again is according to the relative laws, which is again a disadvantage of acquiring large velocity by the combustion of very rapid combustion of the fuel. So the body of the rocket is made cylindrical and elongated like the shape of a cigar, and its nose is sharply pointed so as to reduce the air pressure on its individual parts to the very minimum. So you have seen the design of the rockets from this figure. It's shaped like this, and its nozzle is made very narrow in order to reduce the air pressure on its sides of the individual parts. Its frame is made of a heat resisting material, and its velocity during the first part of its flight through the denser layer of the air is kept sufficiently low. And the frame of the body or the frame of the rocket is made of heat resisting material. Because the fuel is burned inside the chamber with very high temperature, so it made heat resistant. And its velocity during the first part of the flight through the dense layers of the air is kept sufficiently low for the first part because of those disadvantages described just above. So these are all about the rocket propulsion. This is working on the principle of, this is a law of conservation of linear momentum. This is one we can treat it as an example for the law where the momentum is linear momentum is conserved. Okay.